Hello everyone and welcome to our deep dive into linear regression and correlation. This is a part of our probability and statistics series. Today, we are exploring a fundamental predictive modeling technique that is used across industries. So let's get started. In principle, linear regression is a subcategory of broader area called as regression. Regression analysis is a form of predictive modeling technique. We employ regression analysis to investigate the relationship between a dependent or target variable and also an independent variable or predictor. There are too many types of regression, including linear regression, logistic regression, polynomial regression, stepwise regression, and etc. And today our focus is on linear regression. Linear regression quantifies the relationship between one or more predictor variable and a single outcome variable. It is often called as multiple regression, multivariate regression, and ordinary least squares. So there are two main types, simple linear regression and multiple linear regression. In the case of simple linear regression, we use a single input variable to predict the output. However, in the case of multiple linear regression, it incorporates multiple input variables for more complex predictions. Linear regression assumes a linear relationship. The output changes proportionally with the input. For example, if we are predicting distance traveled based on speed, the faster you go, the farther you travel in a fixed time. What are the applications and use cases of linear regression? Linear regression shines in countless scenarios. For instance, it can predict house price based on size, and it can evaluate marketing campaign success, or it can assess risk in finance and insurance. For example, if you want to rent a house or you want to sell your house, you may go to a real estate, right? So you explain about your house and the dealer tell you a price. This price comes from linear regression, right? Because that guy has experience, and based on the experience, he can utilize his model and predict a price for your house. Other use cases include analyzing consumer behavior, studying car engine performance, or even exploring astronomical data. So far, we have got an intuition about linear regression. Let's get to the math behind linear regression, but don't worry, I will keep it clear. Linear regression models the relationship as a straight line. In other words, linear regression is a linear model. We want to have a model that assumes a relationship between the input variable, like x, and the output variable, like y, right? So in this example, x is independent variable and y is dependent variable, right? As x changes, y also changes as well. So the output varies linearly based on the input. So in here, y is the output that is determined by the input of x. So here we have two other variables like beta 0 and beta 1. Beta 1 is slope, right? So this determines how much value of x has impact on y, and also b is constant, right? So if we want to draw a line, because it's a linear model, we need to have two variables. So the first point is where to start this line, right? From here, right? So these values that we have here, these are beta 0 or intercept. The second point is, or the second property of the line is, what is the slope of this line, right? So the main objective here in linear regression is to find these two, beta 0 and beta 1. Normally, an error term like epsilon is also added here. So we can say y is beta 0 plus beta 1, x plus epsilon, right? Let's consider one example of bicycle riding. Imagine you are predicting distance traveled as y and based on a speed of x. Our linear regression model representation for this problem is y is equal to beta 0 plus beta 1 x, right? Or you can say distance y is the distance traveled, beta 0 plus beta 1 multiply speed, and x is speed, right? So as speed increases, the distance increases. So distance is dependent on speed, but speed is independent. We call this beta 0 as intercept, and we call beta 1 as coefficient or slope. Suppose time is constant in this example, right? For example, in 60 minutes, right? Then if the speed is 10 meters per second, this guy can travel 36 kilometers. If we increase the speed, right? So this is x and this is y. X is speed and y is distance traveled. If we increase speed from 10 to 20 meters per second, then the distance traveled also increases to 72 kilometers within 1 hour, right? And if again we change the speed from 20 to 30 meters per second, then what is the distance traveled? So this is how linear regression works, right? Distance traveled is proportional to speed, right? This is called as positive relationship. So linear regression can model both positive and negative relationship. When time is constant, we can travel longer distance in a given amount of time if and only if our speed is high. So you can see here, this is the speed and this is the distance travel, right? As the speed increases, the distance travel also decreases. This point here is beta 0 or intercept, and this is the slope of this line. Beta 1 is slope of this one, right? So we can write y as the distance traveled in a fixed interval of time is based on speed, right? So this is called as a positive relationship, right? As x increases, y also increases. For example, higher speed means greater distance travel in a fixed time. And for example, if originally the speed is 10 meters per second, we can go to 36 kilometers, right? And if we change the speed to 30 meters per second, then we can go for 108 kilometers, right? On the other side, we have something called a negative relationship. In negative relationship, as x increases, y decreases. For example, for a fixed distance, higher speed reduces travel time. So here it is. In this time, distance is constant. For example, we want to travel only 10 kilometers from point A to point B, right? The distance is constant, right? So then here, our x is speed, our y is time, right? So as x increases from 10 to 20 kilometers, y decreases from 100 seconds to 50 seconds. So the speed is 10 meters per second, and we want to travel 10 kilometers, then we need 100 seconds time, right? If we want, so 110 kilometers is too high, 1 kilometer. If we increase the speed to 20 meters per second, then we can travel 1 kilometer in 50 seconds, right? So y decreases, but x is increasing, right? This is called as negative relationship. As speed increases, time decreases. As you can see here, this is a speed, x is a speed, y is time, right? So as you can see here, x is increasing, the value of x is increasing, but the value of y is decreasing, right? This is called as negative relationship, and y is the time and x is speed, right? So the time taken to travel is dependent on the speed. Normally, an error term is also considered when we want to model individual inputs. That's why yi is equal to beta 0 plus beta 1, xi plus this is called as error term. So the observed value of the dependent variable like yi is composed of a linear function like beta 0 plus beta 1 xi of the planetary variable together with an error term epsilon I. The error term epsilon I, epsilon 1 up to epsilon n, these are generally taken to be independent observation from a normally distributed like n, 0 and variance for some error variance sigma square. This implies that the values y1, y2 up to yn also observation from the independent random variable, and they follow a normal distribution in this way. Yi follows a normal distribution beta 0 plus beta 1 xi and sigma square. In this figure, we can see here a simple linear regression model. Each y has a normal distribution. So these are values for x, these are values for y. If this is x1, then the value of y1 is this one, right? This point. So here we have a distribution. If this is the mean, we have a distribution of y1. Then if this is x2, this value is for y2, and here you can see a distribution of y2. And the same for xn, this is yn, and this is the distribution of yn. Then this line is called as regressor or regression line, right? A regressor. The ultimate goal of linear regression is to find this line, right? Later I will explain more. We want to find a line that minimizes the error. Linear regression assumes a linear relationship, normally distributed error with mean 0 and constant variance sigma square. So the parameters are beta 0 intercept parameter, beta 1 slope parameter, and error variance, so sigma square. The error is the distance between actual and predicted values. Our goal is to find a line that minimizes these errors. Once again, we want to find the parameters, and the parameters are beta 0, that intercept parameter, and beta 1, the slope parameter. And also a third unknown parameter, that is the error variance sigma square, also can be estimated from the dataset. In this figure here, we have x and we have y, right? So these points that you can see here, these x's that you can see here, these are the actual data. Our goal is to find a model or regressor or line that can be a representation of these values, right? So what it means I want to find a model that, for example, if this is x1, then this is y1, right? Then this one should be on this line, right? So then this one here on this line, this one here on this line. So it means I want to find a line that is the best representation of this data. What is the best representation of this data? It means if I find the error between, so this is the error, right? This one is the error. If I calculate this error between every data point and line, it will be minimized, right? So how I can minimize this distance? By changing beta 0 and beta 1. Right? So here you can see here the value of error between, or you can say the distance between the line and each data point is less than here, right? So you can see here the distance between each data point and the line is much greater than this one, right? So for example, for this one is very less. So this one is greater than this one. We have to adjust the line somehow to have the minimized error. Beta 1 can be in 3 points, right? Beta 1 is the slope, right? So if beta 1 is greater than 0, it means the slope is something like this. If beta 1 is equal to 0, it means it's constant line. If beta 1 is less than 0, then it will be negative, right? The slope parameter, like beta 1, is of particular interest since it indicates how the expected value of dependent variable depends upon the explanatory variable x. So in this figure here, we can see a quadratic, or we can say at least nonlinear. This is not linear, right? This is nonlinear. This is a quadratic relationship between the two variables, and it would make no sense to fit a straight line here. So our linear regression works for linear data. It means line, not a curve. So this one cannot be modeled using linear regression. For simple linear regression, we fit a straight line through paired data points like xi and yi. Errors are independent and normally distributed. We estimate beta 0 and beta 1 and also sigma squared to build the model. This is the our simple linear regression model, right? This is in fact a try to fit a straight line through a set of paired data observations like x1, y1, x2, y2 up to xn, yn. Also here we have epsilon 1 up to epsilon n. These are the error terms that they are taken to be independent observation from a normally distribution of z and sigma squared. The three unknown parameters, like the intercept parameter, slope parameter, and error variance, these are estimated from the data set. Let's see one example here. Suppose in a car manufacturing, we want to see the relationship between the electricity usage of the manufacturing and the production. So we have a data set here. For example, in the month of January, the company had $4.51 million product, and in that month, they used 2.48 kilowatt electricity. In the month of February, the sale or the production was 3.58 and electricity usage was this one. So we have the production value and electricity usage of 12 months a year. We can also plot our data in a scatter graph, right? So here you can see this value. This is something 3.8, 3.58, and 2.26, right? So this is this data, February, right? And here, this is some other data, right? It's something close to 2.6. We can say this is maybe this one, right? March. These are real data, or you can say data points, right? So our model is y is equal to beta 0 plus beta 1 x, right? So in this example, production is fixed, right? So production is x and electricity usage is y, right? So this is independent variable and this one is dependent variable. It means the amount of electricity usage is based on the production. The regression line, like y is equal to beta 0 plus beta 1 x, is fitted to the data points like x1, y1, x2, y2, xn, yn by finding the line that is closest to the data points in some sense. So here we can see our data. So for example, this is our data. This is the actual data, and the predicted based on this regressor is this one, right? And this one is here. This one is here. So distance here is called as error, right? So this is the distance between each data point, and so here is the actual and here is the predicted. Then this fitted line is chosen to be line that minimizes the sum of the squares of these vertical deviations or errors. Then here we have least square fit, that is q is equal to I from 1 to n, yi minus beta 0, yi is the actual point. Actual data point, right? And this is the predicted data point, right? Predicted square. This is called as least square fit. It means actual data point minus predicted. So far, we studied the basics of linear regression. The main goal is to find the best parameters. It means we want to find a line that well fits and will be good representative of our data. This animation well explains the linear regression, right? So these are the data points, and this one are the error, right? So we want to minimize the error, and we want to have a line, and this line must have the less distance with sum in all together between predicted and actual, right? So you can see here, we try to minimize it, right? We want to adjust their intercept and the slope of the line to have the minimized distance between each data point and the line. In the previous slide, we defined the least square fit. We can use the least square fit for parameter estimate, like to find beta 0 hat and beta 1 hat that are maximum likelihood estimate. We can find the PDF of error as 1 by 2 pi sigma error term e in power of minus epsilon I square to sigma square. Then we can find the joint density of the error terms, like from epsilon 1 to epsilon n, as 1 by 2 pi sigma power of n e in power of sigma from 1 to n epsilon I square to sigma square. This likelihood is maximized by minimizing the sum of error square. And this one is epsilon I square is sum of actual data points minus predicted data point, that is Q. We can simplify the parameters by taking partial derivative of Q with respect to beta 0 and beta 1. So first, partial derivative with respect to beta 0 and partial derivative of Q with respect to beta 1, right? So with respect to beta 0, it will be equal to minus 2 I from 1 to n yi minus beta 0 plus beta 1 x. And partial derivative of Q with respect to beta 1 is equal to minus 2 I from 1 to n xi yi minus beta 0 plus beta 1 xi. So we can estimate beta 0 and beta 1 by solving these two equations. So sigma I from 1 to n yi is equal to n beta hat 0 plus beta hat 1 sum of all xi from I to n. And also the sum of xi yi is equal to beta hat 0 sum of all xi and beta 1 hat sum of square of xi. These two equations are known as the normal equations. So using this normal equation, we can find beta 0 and beta 1, as I will explain in the next slide. So we solve the normal equation to find beta hat 1 and beta hat 2. Beta hat 1 is equal to n multiply sum of multiplication of xi and yi minus sum of all xi multiply sum of all yi divided by n sum of xi square minus sum of xi all square, sum square. In here, sum of each data point square. In here, we first do the sum, then square. Then beta 0 hat is equal to sum of all xi divided by n minus beta hat 1 that we found here into sum of all xi divided by n, and this is y bar minus beta hat 1 x bar. If we want to make it easier to understand, we will define sxx and sxy, right? So these are two variables. They help us to better understand the topic. Sxx is simply sum of each data point minus mean square, right? Each data point minus mean square, and it is equal to sum of xi square minus n x bar square, right? And we can write this one as sum of xi square divided by n, right? Then we can define something as sxy. Sxy is sum of xi minus x bar, yi minus y bar, right? Mean. Then this one is equal to xi multiply yi minus n x bar y bar, and that is equal to sum of xi multiply y minus sum of all x, sum of all y divided by n. The next parameter that we need to estimate is the error variance. The error variance, sigma square, can be estimated by considering the deviation between the observed data values yi and their fitted values y hat, right? So these are the observation actual data, and these are the fitted value y hat I. Specifically, the sum of a square for SSE is defined to be the sum of the squares of these deviations. So SSE is equal to I from 1 to n yi minus y hat, right? Their fitted value y hat I, which is equal to, instead of this one, we write this formula, right? So it will be sum of yi minus this beta 0 plus beta, the linear model that we have. And this one we can write in this form, that it is equal to sum of yi squared, because we have a square here, minus b multiply yi minus beta hat 0 multiply yi minus beta hat 1 multiply xi yi. And that's why we can write that the sigma square is equal to SSE, this value, divided by n minus 2. Our goal is to find a fitted line, that regressor. So we can easily do it by knowing some variables. First, n. We need to know the n. We need to know the sum of all xi. We need to know sum of all yi. We need to know sum of all xi square, yi square, and xi multiply yi, right? So we can simply do it. Xi is sum of all x values based on this table that we have, right? X is production, so this is x. This is x values and these are the y values, right? Sum of all x values is 58.82. Sum of all y values, this one. Then xi square, then you sum up them together, right? Then this value. Then y square, each y value square, then you sum up them together, this one, right? And this case, each x multiply y. So x1 multiply y1, x2 multiply y2, up to x12 multiply y12. So this is x1, y1, this is x12, y12, right? And you sum up them together, this value. The estimate of the slope parameter and intercept parameter will be very easy. Just we put them in the equation. So our n is 12, right? We have 12 months. Then sum of xiyi. Sum of xiyi is this one, right? So we have this one. So 12 multiply this one. Minus sum of xi. Minus sum of xi, 58.62, right? So 58.62. Then sum of yi. It is 34.15, 34.15. Then n, again 12, multiply xi square. Xi square is this one, minus xi square, sum of xi, this one is square, right? And then if you do this one, you can come up with beta hat 1 as 0.49. Next, based on the equation, beta hat 0 is equal to y bar minus beta 1 hat x bar. Here, for this one, sum of all y values, 34.15 divided by 12n, right? Minus this value that we found here, multiply x bar, all x, so sum of all x, this one divided by n12, then you can find 0.490, right? So we found the line. This is the line, that is the regressor. So this is the regressor, right? So regressor is y is equal to beta hat 0 plus beta hat 1 x. It means the starting point of this value is point. So this is the intercept, and this is the slope of line. What is the use of this regressor? This is the regressor. This is the model that we have generated. What is the use of this one? If we want to predict something, right? So we had these values from, for example, January 2024 to December 2024. Now, based on this data, we want to predict the January 2025, right? It means if the production is $5.5 billion, then what is the amount of the electricity that we need to use, right? So we put it in formula, this one, and instead of X, we will put this one, right? So if the company wants to have $5.5 million product, the electricity usage will be 3.15 kilowatts something. It seems that this model is not good for all values. It means that this model is good for production level between 3.5 million up to 6 million. Using the model for production values like X out of this range is known as extrapolation. So if we want to use this model for out of the range like 3.5 million and 6 million, we call it as extrapolation, and it may give inaccurate results. For example, suppose that the production is going to increase to 8 million, right? 8 million, then if we calculate based on the equation, we come up with 4.401. But it seems not to be correct because 8 million is out of the range that we decided, right? Based on the example, the range was something like 3.5 up to 6, and this 8 is out of this range. For this problem, the error variance is estimated like this. The error estimate is sum of all yi square minus beta hat 0, sum of all yi beta hat 1, sum of all xiyi divided by n by 2. Then again, sum of y square this one, beta hat this one, sum of all yi this one, minus beta hat 1 this one, xi this one, and 12 minus 2 is 10, then you will come up with this one, and the error is this value. Inference on the slope parameter, beta, is the next topic that we want to discuss here. So far, we try to estimate our parameters like beta 0 and beta 1 and the error variance. However, it seems that beta 1 is more useful because using beta 1, we can determine the nature relationship between x and y. Now, we want to make some confidence interval for slope, and then we try to test hypothesis that the slope parameter takes a certain value. Indeed, beta hat 1 is a linear combination of normally distributed random variables yi, and it has a normal distribution like beta 1 hat follows a normal distribution with parameters beta 1 and sigma squared divided by sxx. Then here, a two-sided confidence interval with confidence level of 1 minus alpha for the slope parameter in a simple linear regression model is based on this one. Beta 1 falls into this confidence interval. Beta hat 1 minus critical point standard deviation of beta hat 1, and beta hat 1 plus critical point multiplied standard deviation of beta hat 1. Then we can say that beta 1 falls into beta hat 1, this one, sigma square critical point divided by root square of sx and plus this value. Then we can go for one-sided from minus infinity to the upper bound and from lower bound to the plus infinity. Now we define our two-sided hypothesis. Null hypothesis says beta 1 is equal to b1, and alternative hypothesis says beta 1 is not equal to b1. For a fixed value b1 of interest, they are tested with the t statistics, where t is equal to b hat 1 minus b1 sigma hat sxx here. Then we can find the p-value. P-value is to multiply probability of x greater than absolute value of t with n minus 1 degree of freedom. So in here, the random variable x has a t distribution with n minus 2 degree of freedom, and the size of alpha test will reject the hypothesis if t is greater than critical value with degree of freedom minus 2. So here we can see the one-sided hypothesis. Two cases we have. In first one, we consider that beta 1 is greater than b1. In here, beta 1 is less than b1, right? And here, the alternative hypothesis is beta 1 less than b1. In here, alternative hypothesis says beta 1 greater than b1. Then in this case, p-value is equal to probability of x less than t. In here, probability of x greater than t. In here, we reject the null hypothesis if x is less than t alpha and n minus 2. In here, if t greater than t alpha and n minus 2. For example, car plant electricity usage that we have already. Sxx is equal to sum of I from 1 to 12 months xi squared, right? It's minus sum of xi squared divided by 12, right? So we already found this one as 291.23, and this one, and 12 is 12, then we can get Sxx as 4.8. Then the standard error of beta hat 1, it is equal to sigma hat divided by root square of Sxx. We already found sigma hat here, 0.17. Then here we use it 0.17 divided by this one here and this value. Then the t statistic for testing the null hypothesis is it's 0. Null hypothesis beta 1 is equal to 0. T is beta hat 1 divided by standard error of beta hat 1. So this one we already found, this one here, and 6.37. And the p-value here is to multiply x greater than 6.37, which is almost equal to 0. Our random variable x has a t distribution and degree of freedom 12 minus 2 is equal to 10. Our p-value is equal to 0. It means that the null hypothesis is not plausible, and the slope parameter is known to be non-zero. So in here, we found that the p-value is close to 0. It's not exactly 0, but it is close to 0, right? And in here, we reject the null hypothesis. The null hypothesis says beta 1 is equal to 0. When beta 1 is equal to 0, it means there is no linear relationship between y and x, right? But we reject this null hypothesis and we conclude that the distribution of electricity usage depends on the level of production, because rejecting the null hypothesis suggests a significant linear relationship between the two variables. It means there is a significant linear relationship between production and electricity usage. So if we have alpha as 0.005 and degree of freedom of 10, and it is equal to 3.169, then a 99 two-sided confidence interval for the slope parameter is this one. Beta 1 falls into beta hat 1 minus critical point multiplied the standard error of beta hat 1 and plus this value, right? So we can go for confidence interval, just we apply the values up to here and up to here, then you sum, it will be 0.251 and 0.747. According to this result, we can confident that within the range of a dataset, the expected electricity usage increases by somewhere between a quarter, 1/4 of a million kilowatt hours, and 3/4, like 3/4 of a million kilowatt for every additional 1 million of production. The next step is to make inference on the expected value of the dependent variable. In fact, we want to make inference on the regression line. As the ultimate goal of the linear regression, we want to do some prediction for our explanatory variable, or you can say x star. Means we want to come up with a line like beta 0 plus beta 1 star. Then in here, a 1 minus alpha confidence level, two-sided confidence interval for this beta 0 plus beta 1 x, the expected value of the dependent variable for a particular value like x star of the explanatory variable is this one that we can find. This value beta 0 plus beta 1 falls into beta 0 plus beta 1 x star minus the critical point standard error of this value, right? Then this value plus critical point with degree of freedom of 2, standard error of this one. Then we can say that the standard error for these two is equal to sigma hat that we found already, root square of 1 by n plus x star minus x bar squared divided by sxx. Then we're gonna find the one-sided confidence interval. Again, what we did, minus infinity to upper bound and lower bound up and plus infinity. Then the hypothesis test on beta 0 plus beta 1 x star can be performed by comparing the t statistics. So t is equal to beta 0 plus beta hat 1 x star minus beta 0 plus beta 1 x star, and the standard error of this one. This is this t distribution with n minus 2 degree of freedom. The standard error of the point estimate like beta 0 plus beta 1 hat x star is equal to sigma hat divided by root square of n. From this, we can somehow understand that the accuracy of the regression line is high at the center of our data set and less accurate towards the end of the data set. So let's take our example for this scenario. That example was car plant electricity usage. So standard error of beta 0 plus beta hat 1 x star is equal to sigma hat 1 by n x star minus x bar divided by sxx. We already found that sigma hat is 0.17, 1 by n 12, x star minus x bar mean square divided by sxx. So with the t of 0.025 and 10, we get the value of 2.28. So here the degree of freedom is 10, and for 0.025 it is 2.228. So this is the value for t value, and we're going to find 95 confidence interval, right? So beta 0 plus beta 1 x star falls into these two values, right? 0.409 plus 0.499 x star minus 2.28 t, multiply the sigma hat, multiply 1 by 12 x star minus this x bar divided by sxx, and this one plus this value, right? Then here, if x star is equal to 5, then beta 0 plus beta 1, it falls into this interval, right? And this value, right? Finally, we can say that this one falls into 2.79 and 3. So this is the 95 confidence interval for x star is equal to 5. We can conclude from this interval that with a monthly production of $5 million, the expected electricity usage is between 2.8 up to 3 kilowatts. This is a regression line that we found for our data sets, right? These dots are the actual points, and this is the line, the regressor line. So also these dashed are the confidence bands. We can see that the confidence bands on the fitted regression line that we calculated for the 95% confidence interval. I already emphasized that the regression line has a high accuracy at the center that you can see here. It's closer. Here, the confidence interval is narrower in here. For example, x is equal to x bar as 4.885, that x bar that we found already. And then the interval becomes wider toward the edge of the data that you can see here. The next topic that we need to study is the prediction interval for future response values. In here, we are going to form a prediction interval for the future response values for yx star. It means when we have a new coming data point, what values may we get for our dependent variables? We know that the value that we get for yx star is composed of a point on the regression line of beta hat 0 plus beta hat 1 and also an error term. We also know that the error term comes from an observation from a normally distributed with mean 0 and variance sigma square. To form confidence interval for this y and x star, we need to take care of two things. One, uncertainty in the value of regression line and variability in the error term. By considering all these things, a 1 minus alpha confidence level two-sided prediction interval for yx star, this is a kind of future value for a dependent variable for a particular value of x star of the explanatory variable. So this is a new value, right? This was not in our data set. We want to predict this one. We want to utilize the Bayes regression model to predict for this value. This one falls into these two values. Beta hat 0 plus beta hat 1 x star minus critical point sigma square and 1 divided by n x star minus x bar square sxx and plus this value. And for one-sided, minus infinity to upper bound and lower bound to plus infinity. Then again, we check our example. So we already found that t value for 0.025 and 10 is 2.228, a 95 confidence interval, and we want to try this one. We already have found these values, and we just put in our equation. So x bar is equal to 0.49, this beta hat 1, so beta hat 1, beta hat 0, beta hat 1 x star minus 2 this t value multiply sigma square multiply 13 n plus 1 n x star minus x bar 2 divided by sxx, and you can find this lower bound and this is the upper bound. Then for x star, if it is equal to 5, then the y falls into this interval, right? Is this one 0.49 based on the equation. Beta hat 1 multiply 5, this x star, minus 4.9, this one. So this is the lower bound, this is the upper bound, and this value. From this interval that we found here, 2.5 and 3.3, we can conclude that if the production target of the next month is $5 billion, with 95% confidence, the electricity usage of the next month will be something between 2.5 and 3.3 kilowatt. The next important topic that we need to study to better understand the linear regression is the analysis of variance table. Analysis of variance is called as ANOVA, right? If we want to make ANOVA table, we need to have the variability in the dependent variable y, and also we need to check a hypothesis test like H0 as beta 1 is equal to 0. To do that, first we need to understand sum of square decomposition. Here we define total sum of squares, or SST in short. This is the sum of square of the difference between real and mean. So these are the real data points and the mean, right? So sum of them, if you minus square, then sum of them is known as SST. In fact, SST is the total variability in the value of y, so we can also show it as SYY. And the degree of freedom is n minus 1. Then so in here, we can see this diagram as the sum of square decomposition for a regression analysis. We can divide this SST into sum of square of regression, SSR, and this is with 1 degree of freedom plus sum of square for error, or SSE with 2 degree of freedom. SSR is to calculate the amount of variability independent variable, so predicted minus mean, right? And SSE, on the other hand, measures the variability about the fitted regression line, yi minus predict. Here, we can see the source of variability for the sum of a square for a simple linear regression. If this is the mean, right, and these are y1, y2, y3, y4, y5, something, right, and this y have here, then this value, this distance is the distance between each data point and the mean, right? In here, we can see y hat minus yi, right? So this is actual, this is the mean, and this is the predicted, right? So this distance is called as SSR. So this is the actual, this is the predicted, and mean also here. This is the difference, right? For this case, for example, this is the actual data set, this is the predicted, and this is the mean, and SSR is this value. Then for SSE, we have yi minus y hat, right? So this is the actual data point, this is the predicted, and this distance. Actual point, predicted, this distance. Actual point, distance. Actual point, and this distance. This is called as SSE. We define the proportion of the total variability independent variable as coefficient of determination, or R square. We already know SST, SSR, and SSE, right? So SST is sum of yi minus y mean square sum all together. SSR is predicted minus mean square. SSE is yi minus y hat. It means actual minus predicted square. R2 is SSR divided by SST. SSR divided by SST. Or you can say 1 minus SSE divided by SST. So once again, the total variability in the dependent variable is the sum of a square of these yi minus y mean. These can be partitioned into variability explained by the regression line, and the regression sum of a square is y hat I minus mean of y square. And the variability about the regression line, the error sum of a square is yi minus y hat I square. Then the proportion of the total variability accounted for by the regression line is the coefficient of determinant, or R square. Then the proportion of the total variability is SSR by SST. This is takes values between 0 and 1. If it's closer to 1, it means if it is closer to 1, the smaller is the sum of squares for error SSE in relation to the sum of square for regression SSR. So we can see this one, this figure, larger value of R square, it means we have less error, right? You can see here, data points are very close to line, then we have larger R square. If we have a smaller R square, it means the distance between data points and regression line is more. So this is more accurate compared to this one. So if we have close to 1 R square, it means better model. The last but not least is the correlation analysis. We know that correlation is the measurement of association between two random variables, and we say, for example, rho is equal to correlation of x and y, which is equal to covariance of x and y divided by root square of variance x variance y, right? The sample correlation coefficient, or R, that we show it by R, for a set of paired data observations like xi and yi is equal to sxy divided by sxx syy, right? And we already calculated that sxx is sum of x minus mean, y minus mean, sxx, so this is xsy, sxx is xi minus x bar, and syy is yi minus y bar, right? Then this one, we can write this one as sum of xi yi minus x bar y bar, and this one xi2 minus nx bar, and y minus ny bar. These measure the strength of linear association between two variables, and this can be thought of as an estimate of the correlation or rho between the two associated random variables like x and y. Under the assumption that x and y are random variables and they have a bivariate normal distribution, then a test of hypothesis says rho is equal to 0 for the null hypothesis. This can be performed by comparing the t statistics. T is equal to r n minus 2 and 1 minus r2. So this is for the t distribution and n minus 2 degree of freedom. In regression framework, this test is equivalent to the h0 and beta 1 is equal to 0. So here we can have different correlation coefficient R. The sample coefficient can take values from -1 to 1, right? So the possible value for correlation coefficient is -1 to 1. It means how related are two variables in terms of trend. 0 means there is no correlation between two variables, right? So this one is the 0 correlation, right? We cannot see any relation between x and y. If this is x and y, we cannot see it. So when this is positive, right, it means that there is a positive association between two variables. It means as x increases, y also increases. So this is 0.3, right? But you can see 0.6 is more, this trend is more clear, right? And this one is more clear, right? So this is 0.9 correlation. And in here, we can see negative correlation. So this is the opposite side of this one, then this one, and then this one. So this is a strong negative correlation. So when it is positive, it means that there is positive association between two variables. And when it is negative, it means as one increases, the other one decreases, right? So as x increases, y decreases here. As x increases here, y increases as well. Now we're gonna find this SST, SSR, and SSE, and also R square for our example. To do that, I'm gonna do it in two ways, using Excel file and also using Python, right? First, I'm gonna try it using Excel. So we have some data, and these are our data. This is about production and electricity usage, right? X and Y. So let's resize this one to 12. Then this is for different month, and this is X. X is production, and y is electricity usage. So the first thing that we need to do is to find sum of all x, right? So sum of all x, and also we do the same for sum of all y. So this is sum of x and y. Then I need to find xi multiply yi. So xi multiply yi. It means each point of x multiply each point of y, right? So this is multiplication of x and I, and this is a sum of xi multiply yi. Next, I'm gonna find xi square, xi square, right? It means each point of x in power of 2. So we'll do the same for all, and we copy paste this one here. The next thing is y bar, right? So y bar is the average of y, so it's equal to average of all y values. So this is average of y values, and because this is the same for all, so I'm gonna fix this one. So I use $sign, so I will have the same values for all. This is the average. Now I need to calculate yi minus y bar. It means each data of y minus y bar, right? That's okay. So we will find the sum. We will find the sum for this one as well. And next, I need to go for x bar. X bar is average, right? So it's equal to average of all values of x. And again, I'm gonna fix these things using $sign. Then average of x, and then here xi minus x bar. Xi, each value of x minus x bar. This one we will sum up together, and we will paste this one here. The next one is xi minus x bar, and then yi minus y bar, right? So it means then here, this value xi minus x bar, this one multiply yi multiply y bar, and then we will do it and we will calculate the sum for this one. The next one is xi minus x bar square. Xi minus x bar, and this one square. It means this one square. Right? Then the next one, yi minus y bar, then a square. It means this one square. Right? And then the next one is y hat, right? So y hat is, we need to calculate the beta 1 and beta 0. So beta 1 is equal to the sum of this one, xi minus x bar, yi minus y bar, divided by xi minus x bar square. So this is the value for beta 1. Then beta 0 is equal to y bar minus this one that we found beta 1 multiply this one, right? Also, we have another equation for beta 1 and beta 2. I will calculate it here. First, we need to find n. So n is equal to the number of data that we have, which is equal to 12. Then we need to find a sum of xi multiply yi. So sum of xi multiply yi. So this one is equal to this one, right? Then sum of xi, which is equal to this one. Then sum of yi, which is equal to this one. And then need to find sum of x underscore I square, right? Sum of xi square is this one. And next, we need to find sum of xi, then all square, right? It means this one in power of 2. Now we can find the beta 1. So beta 1 is equal to n is equal to n, this one 12, multiply sum of xy, then minus sum of x, multiply sum of y. This is the upper side, and the lower side is equal to n multiply sum of x2 minus sum of xi square, right? That's okay. Then beta 1 is this one divided by this one. So this is beta 1, and beta 0 is equal to sum of y, this one, minus beta 1 multiply sum of x, and this all divided by n. So you can see here we found beta 0 and beta 1. Now here we can find y hat. So this yi minus y bar squared, this is known as SST. And for y hat, this one is equal to beta 0 plus beta 1 multiply this one, x value, right? So we can do this one for all. And we need to fix these two. So dollar sign, then dollar sign, and we fix all. Then again, this one here. Next, SSR is equal to y hat minus y bar square. So it is one y hat minus y bar, and this one square. That's right. SSE is equal to yi minus y hat squared. Yi is this one minus y hat this one, and square. That's correct. So we already found that our y hat is equal to beta 0. Beta 0 is 4.09 plus 0.49 multiply x, right? This is the regressor or regression line, right? Then we found our SST. SST is equal to this one. SST is equal to this one. This one is SST. Then SSR is equal to this one. And then SSE. Then SSE is equal to SST minus SSR, right? So SST minus SSR. So this is the same that we found here. Same, it's been correct. Now R square is equal to SSR divided by SST. SSR, this one divided by SST, 0.8. Another way of R square is 1 minus SSE divided by SST, right? So it will be equal to 1 minus SSE, this one divided by SST. So the same value. And for prediction, for example, we want to do prediction of a new x, right? And x is equal to 5.5, right? So the value for this one, the y hat, is equal to this one plus this one multiply 5.5. So it is 3.15. Then we need to find the correlation, right? So correlation, or R. So this one is equal to xi minus x bar. So this one is equal to xi minus x bar. This one is equal to SQRT of this one, xi minus x bar. And the next one is equal to SQRT of yi minus y bar. That's correct. And now R is equal to this one divided by this one multiply this one. And it is 0.8. So this is the correlation coefficient of this linear regression. All right, so let's try the same example in Python. For that one, we need to import numpy as np. Then we need to import matplotlib.pyplot as plt. And also from scipy, we need to import stats. That's right. Then we need to pass our data. So production is equal to np array. And here we're gonna pass our data 4.51, 3.58, 4.31, 5.06, 5.64, 4.99, 5.29, 5.83, 4.7, 5.61, 4.9, and 4.2. The same thing that we do for electricity, and electricity is equal to numpy array. And here we have 2.48, 2.26, 2.47, 2.77, and then 2.99, 3.05, 3.18, 3.46, 3.03, 3.26, 2.67, and 2.53, right? Some problem is here, the comma missed. That's correct. Now we're gonna get the length. The length of any of data is okay. So length of production, for example, and we're gonna print n. So we have 12 data. Then we're gonna calculate x mean. X mean is equal to np.mean of production, and also y mean is equal to np.mean of electricity. Then we can print x mean and y mean, right? So 4.88 and 2.84. Next, I want to calculate beta 1 and beta 0. For that one, first I get the numerator. Numerator is equal to np dot sum of production minus x mean multiply y values minus y mean. And denominator is equal to np sum of production minus x mean, and this one in power of 2. Then the beta 1, or slope is equal to numerator divided by denominator, which is 0.499. Then here the intercept is equal to y mean minus slope multiply x mean, which is 0.49. Now I can go for prediction of y values, right? It means I use this model and for prediction of each x value. So y prediction is equal to intercept plus slope multiply every value of production, right? And I can print intercept, right? And now I can print y pred. So these are the prediction values for each value of x. Next, I'm gonna print SST. SST is equal to np dot sum electricity minus y mean square. SSR is np sum of y pred and y mean, and the SSE is electricity minus y prediction square, right? So then I can print SST. SST value is 1.5. I can print SSR. SSR is 1.2, and print SSE, and this is 0.29. And then I can calculate the R square. R squared is equal to SSR divided by SST. so which is 0.8, right? And also I can calculate R as relation coefficient. This is the numerator divided by NP is to RT of denominator multiply SST and print R, which gives us right 0.89. And also I can use this one for prediction new value. So prediction of, for example, for NP array of 5 and 8, then here prediction is equal to 2.9 and 4.3. Then I can plot it. So PLT scalar, and in here I'm gonna add production, then electricity, and then color is equal to, for example, blue, and label as data. Also, I can print the regressor line. So you can see here is the data. So these blue dots that you can see here, these are every data point that we have, and the red color is the regressor line. Okay, that's it for linear regression and correlation. We have covered definitions, applications, math, parameter estimation, inference, and correlation. These tools power prediction everywhere, from factories to real estate. Please feel free to leave your questions as comment below this video lecture. Thank you, and see you in the next lecture.